Dr. Kathrin from Quantinuum, who's a quantum evangelist today. She's going to talk about TKET and Quantinuum's Advanced Quantum SDK software development kit for the NISQ era. We're very lucky to have her, and thank you for joining us, Kathrin.
Well, thank you very much for the invitation. I'm super excited to have a guest lecture today and tell you about TKET. I'm seeing a chat, so I'm assuming that I'm probably not going to be able to answer the chat while I'm speaking, but if you can moderate that for me, that'd be great. So
yes,
we can just keep the questions to the end. That works for me, if it also works for you. Okay, so let's get started. First of all, I want to open, you may have heard that we just launched our new H2 chip, and we demonstrated a new state of matter, which is a non-abelian topological order state. So pretty much the fancy way of putting this is we can potentially use our trapped ion qubits to make fault-tolerant qubits. So that's what this big work is about. So fault-tolerant quantum computing comes maybe earlier than we thought. We'll see. There's still a lot of research to be done if this state we created can indeed be used as a fault-tolerant, qubit. So very exciting times. So this is our new chip, which you see here is our erase track, and we're very excited about that. Quantinuum is the largest quantum computing company that stands by its own. You have IBM, Google, Microsoft Azure and such, but we are they're like integrated into like a big company, but Quantinuum is its own full stack company, and we are the largest. We're around almost 500 employees, and we are continuing to grow. We have offices all around the world. And I am right now in Broomfield, Colorado. So I'm in the building where we have our new H2 hardware running right now. So it's very exciting to be so close to our newly released quantum computer. So if you have not heard about Quantinuum, we are a full stack quantum computing company. Pretty much we are offering everything from algorithm development to our hardware, which is our H series. But we also have a middleware called TKET, which is our quantum software development kit. It's open sourced. And TKET is kind of the glue between allowing users to use any kind of language they would like to use, like Qiskit or Cirq or Q#. Then they can use TKET as a compiler and then run it on the hardware they would like to run the quantum circuit on, or the quantum algorithm. It could be our H series hardware, but it could also be IBM hardware, for example, or other superconducting hardware if you wish. So gate-based quantum computing, TKET right now is one of the state-of-the-art compilers. So I want to talk today about TKET, its features, and how you can integrate that into your research studies and your learning of quantum computing. So let's go into this quickly so that you know that there are different types of hardware out there. Superconducting with IBM, ion traps, that's IonQ or Quantinuum, AQT. You have photonic devices, but you also have other technologies. So pretty much you have all these different types of hardware, and what you are right now kind of thinking about is like how many qubits do you need, how good do the qubits have to be, and you may know, for example, that superconducting qubits, you have the IBM Osprey, right, has a qubit record, but when you do research, you also have to look at something called quantum volume, which is kind of like a measure of how many qubits you can use. It's kind of like how many qubits and how deep can you go with your quantum algorithm, how many layers can compute, and quantum volume is something also you hear about. And it turns out that the bigger the quantum volume is, the more computational power your machine has. And Quantinuum, the hardware we have, our H series, you can see here compared to IBM, we have a very good quantum volume. So we don't have as many qubits, but our qubits are really good. So the quantum volume right now is like 65,000, which is a pretty big number. But in any case, we are trying to increase this quantum volume by tenfold each year. If you're interested in the data, you can just take this snapshot of this QR code. But pretty much when you have all these backends, you have to think about what hardware you use, what resources do you need? Do you need a fast computer? Do you need a computer with high fidelity and such? So in any case, you have a lot of options. And I don't want to go through this right now, our hardware roadmap, but I want to go into pretty much what interests you as a user. So imagine you're a quantum information scientist, and you want to have your gate level quantum algorithm you want to use to solve your problems, right? And you want to have this gate-based quantum computer to solve it. You want to program in your favorite language, which might be, Qiskit, Qsharp, or Cirq. You want to run your algorithm most efficiently on your backend, and you want to get the most accurate results. So that's the goal you have in mind when you go and use quantum computers. But when you do that, nowadays you have to think about some things, be aware of limiting things on your quantum computer. So as you know, we are right now in this noisy intermediate scale quantum era, which we call NISQ era. So we have like 50 to 100 qubits. They have pretty still high error. Coherence time might not be ideal. Connectivity is not fully depending on which machine you use. So you have all these constraints you have to think about. And typically, we work with small circuits, especially if you have to do hybrid computing with classical computation involved into it. For example, a VQE. If you do that, it's like hybrid computing with a classical computer. So anyways, you are in these areas where you have constraints, and the NISQ algorithm has its constraints. So when you are thinking about errors, for example, you can have 2-qubit errors, for example, 2-qubit gate errors, where you have entangled 2 gates. You can have single qubit errors. You have errors when you measure out your circuit. You have errors, other errors in your system that are correlated, for example, that are time dependent. But the most ones that are most budget unfriendly for your error budget is the 2-qubit gate fidelity. So when you're doing your project, you can always think about, and then you pick out your hardware, you should think about how much can I actually run on the hardware. So you could take, for example, the 2-qubit gate fidelity. So 1 would be perfect. That's what we're shooting for when we talk about fault tolerant quantum computing. But we're not at 1. We are like at 0.991, which is 993 is a superconducting era, and 0.996 to 0.98. That's kind of like a trapped ion, 2 qubits fidelity. And then you can think about how many 2 qubits do you have, qubit gates do you have in your circuit, and you can think about what's the total error, 2 qubit error you are happy with. Say, for example, your total error should be more than 25%. Then you can say, oh, if I have a quantum computer with this 2 qubit gate fidelity, I can maybe do 30 2 qubit gates. But if I am able to use a trapped ion quantum computer, I possibly could do like 142 qubit gates, right? So gate fidelity is really important to keep in mind when you do experiments, which quantum computer you use, because if your circuit has more than 60 or 70 2 qubit gates and you have a superconducting device available to you, you're getting a lot of error pretty quickly. So that's one thing you have to consider when you run your quantum algorithms. Then also you have to consider the hardware architecture. So here I show you a couple of superconducting devices, and I want to tell you that the connectivity depends, right? So certain qubits here, this qubit can talk to this qubit, but when you want to talk to this qubit here, you have to apply swap gates, which are very expensive 2 qubit gates in order to talk to these two qubits can talk to each other. So you have to take your algorithm and it has to fit on this architecture. And then depending on which quantum computer you have different basis gate sets. So as you know, learned by now, when you have a gate, right? For example, a Hamiltonian, you apply to your qubit. It is a rotation on the Bloch sphere, for example, but in your quantum computer, you have to perform this rotation. And typically, a quantum computer does not have a Hadamard gate. A quantum computer has a basis set that can take that Hadamard matrix and rewrite it into the gates the quantum computer can perform. So you need to rebase your Hadamard gates into these basis gate sets. And then you have to take your algorithm and it has to fit on this architecture the most efficient way that you don't have to do too many swap gates that are very expensive, because these are 2 qubit gates, and 2 qubit gates, the swap gates are typically 10 times more noise prone than single qubit gates. So you have to keep all these things in mind. And then also here you notice for IBM, all of these qubits has a different color. So each of these qubits have a different noise. So when you take your circuit, you probably want to put your circuit onto like qubits that have less noise, right? So that's what you would like to do. So you would maybe want to be right here. Actually think about, should we do a laser pointer? So you want to maybe, put your circuit onto these qubits because they have lower noise compared to putting your circuit on these qubits where you have higher noise. So you have to consider all these things, but you don't really want to like bother with all these details. So classically, the way you can go about that, you can take your most favorite language and then apply it to your machine, not worrying about all these errors or all these limitations. We have something called a classical computer, which is a compiler. So the compiler takes a high-level language, which we like, could be MATLAB, for example, or Mathematica. You type up your problem, you click enter, you have your compiler, and the compiler takes it then to your machine, which puts it in machine language. The machine is then doing the computation, and then you get the message back, and then you can read the result in your most favorite language. So TKET now was built with the same idea in mind, that you have any kind of language you would like to use, like Pennybain, Q#, Circ, physics, for example, for ZX calculus. You send that to your compiler. In this case, it's TKET. And then TKET will then send it to the hardware you have available, which you want to use. But it takes all of these things. How do you place your circuit? How do you make the circuit very small to have the smallest error and such into account for each of these backends, so you don't have to worry about it. So ideally, you can make an algorithm, you can run it on any backend you want, and you don't have to worry about making it most efficient for your hardware. TKET is doing that for you. And TKET is written in C++, so it's a very fast compiler compared, for example, to Qiskit, which is mostly written in Python. So it's a little bit slower. People are now going to Rust, which may be another way of speeding things up. But because TKET is written in C++, and C++ is not very user-friendly, not many people know how to code in C++, TKET has this PyTKET Python wrapper that allows you to access TKET with your Python code, which is very nice. So what I want to talk about next now is how do you commute, like how you talk to PyTKET if you use any kind of language, your favorite language, and how does PyTKET manage to run everything on on your backend in the most efficient way. So I will go through this now in detail to show you the different features. The slides I have are slides, right, where I show you code snippets, but I will share with you a Jupyter notebook at the end of the presentation where you can then run the code for yourself, okay? So TKET extensions. So TKET, I showed you here, has many different extensions, but I just want to point out that all of these, you do pip install PyTKET for a Python package, but you can also do pip install Qiskit, for example, that you have access to all of the IBM backends, you have access to all of the simulators. You can also do PyTKET bracket, which would do the AWS, for example, PyTKET Q#, that's the Azure backend. You also have access to simulators. So, for example, QJAX, that's a very nice simulator to have for machine learning or quantum algorithm development. There's some other simulators you may be of interest. So PyTKET has extensions for that. And then we have transpilers where you can use, for example, your penny lane toolboxes, and then you can transpile it to the PyTKET language, and then you can most efficiently run it on your different backends or Circ, for example. So PyTKET has many, so we call these ticket extensions. There are over 16, so we probably are very well versed there, and we're still releasing new extensions as we speak. I already said that if you want to use a ticket with the PyTKET wrapper, you pip install PyTKET, and then you pip install PyTKET KSticket and such for all of these other extensions. So it's fairly user-friendly. This is just an example of how you code a PyTKET circuit class. So you import your circuit. It's very similar to KSkitt. This is how the render circuit Jupyter, that's our rendering, to make this a nice circuit diagram. And then you define your circuit. You have 2 classical bits. Then you apply a Hadamard gate to qubit 0. And then, for example, your C0 gate to your target qubit 1. And this is just your initial Bell state circuit. So it's very straightforward, the way to code, just to show you an example. The nice feature about PyTKET is if you have ZX calculus representation, you can actually just click on this button here, and then it switches your whole circuit into ZX calculus. So this is really nice. You can also download your image as a picture, so you don't have to worry about it. In the new version of PyTKET, you also have a dark mode for your circuit. So say now that you have everything developed in Qiskit, this is your favorite language of coding, and you then want to use a TKET as your compiler to make the best out of your circuit. You simply import Qiskit to TKET, and then you call your circuit, and that will write your PyTKET circuit. Or once you do your maybe your algorithm compilation, and you want to put it back into your Qiskit language, you can also go the other direction. So you can take a TKET circuit and you can convert it into Qiskit. And all the other libraries like Cirq and Pennylane are working the same way. So this bidirectional call function you can also do for other quantum circuit languages. Just to give you an example here, so this is your, maybe that's a Qiskit circuit, right? So you have your qubit 0 and 1, Hadamard gate, C0 gate, and then you do your measurement. So now if you code in Qiskit, you import your Qiskit to TKET extension, and then you just call this, right? And then you are plotting this out, and now this is your TKET circuit. So you can see it's fairly straightforward. There's not much you need to do in order to get it into the PyTKET version. So now let's talk about the main part of what TKET is really good at. So maybe I should tell you a little story here. So TKET was initially developed in 2014, and it was specifically developed in mind to be a front-end and back-end agnostic quantum software development kit. So this was specifically TKET was precisely made for this, because people should be using a favorite language and a favorite backend. And TKET will do all the work for you. So we have now almost 10 years of research in TKETs, and we are updating it regularly to the latest compilation research. There's a lot of people in our team that work on doing that. And what TKET really does, besides being front-end and back-end agnostic, and for you, few lines of code you can apply TKET, it really does very well in solving for constraints, so that you can meet the restrictions of your backend and also do circuit optimization. So make the circuit smaller and smaller, so that you have less 2-qubit gates, so that you can actually run deeper and deeper, like algorithms that are very deep. You can make them smaller, so they actually fit on your device, so that you get a good result. So how does TKET do this? So TKET has many, many passes. We call these passes, and each of these passes does something specific. For example, there is a simplification pass that looks at specific structures of a circuit. For example, as you know, any quantum gates we apply on a quantum computer, these are unitary gates. So if you apply 2 unitary gates after each other, if you do the matrix multiplication of these 2 gates, right, the same gates, you will get the identity matrix back. So meaning rather than implementing too expensive 2-qubit gates, you want to look for these and just replace them with nothing in your circuit, right? So that is very cheap, whereas this is very expensive for on a noise model. You also can look at this, for example. You may initially think, well, here I have 1, 2, 3 gates, and here I have 1, 2, 3, 4, 5 gates. So you would think that this has less gates, so it's better for me. But recall that the 2-qubit gates are 10 times more noisy than the single gates, right? So it's better if you can rewrite this, these unitary matrices in another set of unitary matrices where you only use 4 single qubit gates and only 1 2-qubit gate, right? Because a 2-qubit gate is 10 times more expensive than a single qubit gate. It makes sense to rewrite 2 qubit gates in terms of 1 qubit gates and some single qubit gates if you can do that. So in any case, there are many other things you can look at. So TKET does that for you. So TKET has a way of looking at specific sections of your circuit, and it looks at these sections and it tries to find all of these rules to make the circuit smaller, right? To rewrite it better for the noise budget. So for example, here, this is just an example of a certain circuit. For example, if you have 2 gates, right, 2 Rx rotations, instead of doing 2 rotations, it's better to do just 1 rotation, correct? Because then you only have 1 gate, which you just have like the total angle of these 2 rotations. These 2 you don't need. If you, for example, if you have an angle here that doesn't have any, like it's just a rotation with 0 angle, you don't want to do that either. We want to get rid of it. And then, for example, as you know, when you run a quantum computer, we typically read out on a C basis, right? So we project onto the C axis, and then you collapse the wave function onto like 0 or the 1 state on your block sphere. So if you have at the end here on this qubit a C rotation rotating around the C axis, it does nothing to your final result because it's just a rotation over the C axis and you're reading out on the C axis. So again, you can get rid of this gate. So you can just do 1 pass in PyTKET, which is called you import remove redundancy pass. You apply it to your circuit, and that's it. And then if you you also have the measuring function I'm added here, I'm sorry. But in any case, you can see now how these 2 rotations turn out to be like 1 rotation. Also, these 2 were combined. We got rid of the identity matrix, right? So here we got rid of this phase, right? Because of the 0 rotation. And we also got rid of the rotation about the C axis because we're measuring on the C axis. So this is just to show you how powerful TKET can be with a single pass. Then, for example, as I told you, when you are now running a quantum circuit on your actual device, you have to think about this architecture, right? So which qubits are you going to use on the device for your computation? And then you also have to consider about these basis gate sets, because if you have a Hadamard gate, I can't implement a Hadamard gate directly. I have to rewrite the Hadamard gate into these basis gates on my quantum computer. So in TKET, you have something called rebase. So you can import that rebase bus, and then you can define which unitary matrices you want to use, complete set of unitary matrices, right? You can use to rewrite any of your gates. So you can define these, whatever you want, and then you just apply it onto your circuit. You can do the same with placement. So what you can do is you can take your placement path for a given backend, which you define, the architecture of your backend, and then again, same thing, you call it in, you have the graph placement, and then you just apply your circuit, and it automatically does it in the most efficient way that it thinks about how most efficiently to put that on there to have the least amount of gates, and also consider the noise that each of these qubits have. So it does it automatically for you. So TKET has evolved into this tool that is used a lot by Quantinuum researchers. And you should know, as you know by now, Quantinuum researchers, are very good at what they're doing. They're experts in quantum algorithm development. They're experts in running the quantum circuits most efficiently on our hardware. We can do mid-circuit measurement, qubit reuse. We know how to do hybrid computing and such. So the TKET team over the 10 years has developed many passes that are specific for applications. For example, we can do ZX calculus resynthesis. We can do mapping. We can do rewrites for pattern. We can do many qubit operations. If a Toffoli gate, for example, we know how to do very efficient and such. So there are very many passes. And a TKET is actually a very advanced toolkit. So if you ever get about to really do algorithm development and you want to learn how to run your algorithm the most efficient way on a certain backend, you can always reach out to our TKET development team and say, this is my circuit. How do you apply the TKET passes most efficiently to my specific problem? And we really have a lot of tools for advanced users as well. So TKET is not just a tool for you to take your circuit and run it on the backend, but it also has very specific passes that can be of advantage to you, more specifically for your specific project. So you should always talk to us when you are working and get to the point where you work on very advanced quantum computing algorithms. But I think for a starter, when you start to become quantum computing researcher and you are developing your algorithms, for example, in Qiskit, and then you want to run it on a backend in the most efficient way, what you can do is you can use your Qiskit language, and then you add a few lines of code, you convert it into TKET, and then all you have to do after you define your backend is you use this, call this function get compiled circuit, you input your circuit, and then you can set your optimization. So how much do you want to optimize your circuit? We have different levels, level 0, level 1, level 2. Level 2 is default, and it must the most efficient circuit optimization. So for you, when you start your quantum computing journey, for TKET, this might be the best pass for you to use right now. But when you get more advanced, you can look at many of our TKET passes that are specific for your application. So I know that a lot of you probably use IBM, because IBM is amazing for educational outreach. They make, they have Qiskit is an amazing tool. It has a lot of resources, and you can also use the backends. So for IBM, I just want to show you here quickly. For our optimization levels, we have predefined for IBM backends. These are all the passes we call for different levels. So you can see optimization level 2 has the most passes. But you can switch them around. So PyTKET allows you to combine these passes, make your own pass manager, or you can just use the default pass manager. But in any case, IBM backend is very well optimized with our TKET compiler, and you can just use it by default if you wish, or change these passes the way you want. So now let's go to an example so you can actually understand what it is all about. I showed you already how we can look at the circuit structure and say, oh, these two circuits, these two gates are the same. We're just going to get rid of them, or we're going to rewrite this section in a different basis gates because it's just less 2 qubit gates. But this you may have seen before. So this is a chemistry-inspired circuit for H2. It has 1, 2, 3, 4 qubits, right? And you want to fit that onto your IBM backend. If you calculate right now the 2 qubit gates, right, it's 56. So 56 2 qubit gates you have in here right now. So if you would, look back at the table I showed you earlier, you would probably get an error of like 60% error, 50 to 60% error if you run that circuit. So that's not really good necessarily. So you would like to make that circuit more efficient. Wouldn't it be amazing if you could reduce 56 2 qubit gates to, I just say something, 20, right? Because then you would suddenly have 20% error or 30% error, and that would be just better for you if you run it. So what TKET does, besides like looking at these structures, we can make smaller. You also have here this is called the Clifford. So you have these ladder structures, right? So you have this phase gadgets and these Clifford ladders, And they keep coming up every time. So in a chemistry circuit, you're going to see these over and over again. So it turns out that these phase gadgets and Clifford conjugates can be very well rewritten in ZX calculus. So ZX calculus can take this very complicated structure and rewrite it into something more compact. So you can take TKET. TKET looks for these, uses ZX calculus to then find these things and rewrite that in a more efficient way. So you may know about ZX calculus. Bob Cooke. He has done this amazing book, which you may have seen already. So if you want to learn about more of ZX calculus, it's a very good resource. But this is, for example, just to show you. This is one pass in TKET. It's called Clifford Simp pass. You apply it to this initial circuit, which I just showed you here, right? To this circuit. It looks for these structures. And just with one line of code, you are going from 56 to 18 2 qubit gates, right? So suddenly you went from like 60% error to 30% error, right? This is just crazy and just awesome. So I should note here that, this is very good, but we haven't rewritten it yet into like a TK1 gate. That's not a gate the IBM machine can implement. So we still have to rewrite that into the basis set. But that's okay, because single qubit gates are less expensive than the 2 qubit gates. So just to show you that this is in there, so Clifford Simp pass, that's a default pass for your PyTKET pass. So it does it automatically for you already, so you wouldn't have to worry about it. So here now I show you the results. So if you take that specific circuit and you run it on IBM Quiddo, this is a freely available backend to you. I think it has 5 qubits. If you just place your circuit and you route it, you have 56 2 qubit gate. This is the correct. So if you put your simulator, the correct output is 1010 state of a 4 qubit circuit, and you get like 35% time the right result. If you use now the PyTKET default pass, you can reduce it to 19 2 qubit gates, and suddenly your answer is 60, right? So now 60 times out of 100. You get the correct answer. So it really significantly increased the probability of success. And then also, if you note here, the states that are incorrect have less of an amplitude, right? So it also reduces that part, so which is great. So now say you have this awesome algorithm and you just have access to IBM, you run it on IBM, and then you went to Oak Ridge National Lab. That's a way for you to get free access to our H2 or H1, for example, our H series chip. If you do that, you could run it. But before I actually want to do that, I want to show you the Qiskit one. So this is one of the Qiskit preset pass managers. You maybe have worked with that. It's the transpile pass for Qiskit. And if you use the Qiskit compiling pass, you would get 237 2 qubit gates. Right, so TKET was able for this specific circuit to do it better. Again, this is their optimization level. I know Qiskit, you can also play around with the passes, so you could probably do better than this. But I'm just telling you that the default specific circuit, the TKET default pass, was working better than the Qiskit default pass, because TKET really has spent 10 years on being very efficient and making the circuit smaller, right? So 37 2 qubit gates, it's still better than 56, but not as good as 19. So now let's say you have access to the H device, the H series device. So for example, in this case, this is how you call it. So you buy the Qiskit import IBM Q emulator, the backend. In this case, you wanted to use the backend emulator for IBM Bellum. This is how you would call it, right? But if you try to take your circuit and not just run it on a Quantinuum device, all you have to do is you have to import PyTKET Quantinuum extension, and then import the Quantinuum backend, and then define the backend. So with 2 lines of code, you're ready to run it on a different backend. So now I told you before, remember the plot I showed you where when you have 25% error for the 2-gate fidelity, of trapped ion is a lot better right now than for superconducting. But keep in mind, trapped ion quantum computers are slower when you do computation. So Superconducting is fast. It always depends on what you want to do. But for this specific circuit, if you run it on the Quantinuum backend, out of like 100, you get like 92 times the correct answer. And only a few other states have an amplitude. So really for this specific circuit, Quantinuum device is very good because we have such a low, a high gate fidelity, I should say. It's very close to 100%. So anyways, you can see how easily you can go between the different backends. TKET is now a state-of-the-art compiler, and there's a lot of research out there. TKET is compared to other compilers. It's state-of-the-art, and you see many applications. So I should probably update now, but for 2023, I have other publications. I've done a paper analysis on TKET, so there are over 300 to 400 papers on TKET. TKET is also now the default compiler for our H series. So when you send a circuit to the H series, you automatically use TKET to make it most efficient for the H series. But you can use it for other ones like IBM, for example. There is benchmarking papers out there where you look at different quantum SDKs, and you look at different algorithms. For example, the UCCSD, it's a quantum chemistry algorithm, or trotterized quantum dynamics, right? So you take these circuits, these sample circuits, and then you run it with different quantum SDKs with different path managers to make it smaller and smaller. And typically, in this case here, you have physics. So physics, that is the ZX calculus quantum SDK. The further you out, the better you do. So for this specific application, physics was doing the best, followed by the PyTKET chemistry passes, that's specific for chemistry circuits. And then you have PyTKET, which is your default pass. And then you have, Qiskit, and then you have, for example, Circ. So for this specific circuit, it did very well. This is now trotterized quantum dynamics. In this case, you have PyTKET chemistry passes. In this specific paper, they defined the passes outperforming other passes and other PyTKET passes, or like other quantum SDKs. But again, there could be an algorithm where, for example, Qiskit is the best for a compilation. There could be an algorithm where Circ is the best for a compilation. So all I want to tell you right now is, if you have a quantum algorithm and you really care about running it the most efficient way, and you have Qiskit set up, use Qiskit, go ahead, but then also just add the few lines of code and just see if TKET gives you an advantage, right? If TKET doesn't give you an advantage for giving circuit, but on average, it does give you an advantage. But if it doesn't, you didn't lose anything because you just added a few lines of code. You just did your error budget analysis, and you go from there. So TKET should really be something you just add with a few lines of code, independent of what favorite language you use, to just see if you can do a little bit better. And TKET has the ability that you could define your own backend too, with your own basis gate sets, with your own noise level. So you can make actually a noise model if you wish to with TKET. So it's very versatile. There's again a lot of papers out there showing again, IBM is using TKET. So if you actually look at the IBM extensions, it has a PyTKET. It's mentioned for the tools you can use for IBM. CERN has used it. Google has used TKET. So TKET is really something other quantum companies are using. So you should put it in your toolkit as well. So pretty much what I hope that I have told you is that, pip install PyTKET, try it out. It's a state-of-the-art circuit compilation. It's rechargeable. It recharges to your backend. It libraries. It's specific application-specific tools. We have many passes I was not able to talk about. And there's a lot of software built on top of TKET. So for example, our quantum chemistry software in Quanto uses TKET to make the quantum chemistry experiments. We also have Lambec, which is our natural language processor, quantum processor. also uses TKET. We have something called Kermit, that is our error mitigation toolbox that also uses TKET. So we have TKET is a lot of quantum algorithms are built on TKET. I will share these slides with you in the chat in just a bit. But you have all the TKET resources. So we have a GitHub, we have a user manual, and we have a Slack channel. So if you use TKET, join our Slack. Our developers are awesome. If it's during the week, they get back to you within 24 hours. Monday's sitting in the UK. So if you're in the US, there's a little bit of a time difference, but you sitting in the UK, they're really good. They get back to you within 24 hours. So if you have a project and you want to ask a question, I'm using TKET, the default pass, or I'm using TKET using these passes. Is this the best, the most efficient thing for my application? And they will come back and help you. Or you have a question about how to apply something in the TKET library, or you have a question, does TKET do that? They will get back to you and tell you. So join our Slack channel if you are interested to get most out of your quantum circuits. Then most importantly, if you want to use the H series for your project, we have the Oak Ridge National Lab. That's a way for you to, your PI can submit, a project, and then you get free credits. If you don't want to go through your PI right now and just want to play with our backend, you can sign up for free for Microsoft Azure, and you get a few credits for free to try out. Then obviously we have in Quanto and such. So, but you can go to our hardware website. So if you have quantum chemistry, if someone does quantum chemistry, that's our toolbox we have for quantum chemists. But anyways, there are ways for you to sign up and get access to our H series. Also, we do have, careers in quantum computing, and we are a full stack company. So for example, I'm a quantum evangelist. I have a physics PhD, but I'm pretty much doing educational outreach. We have people, in marketing that do work. And then we have people in error correction. We have people in software development. We have people building the microscope optics, right? Laser physicists. We have engineers. And all of these things we're looking for. So this is our website for career opportunities. We have internships. Internships typically open up in, October, November. We have half of our company sits in the UK. So we have European-based internships, and then we have the US-based internships. So if you're interested in an internship, check our careers page, in early fall, and see what comes about for you to go and work at Quantinuum over summer in 2024. But yeah, so this is it. This was my introduction to TKET, our quantum software development kit. And I'm happy now to open up the whole thing for questions.